Okay, so today we're going to do a little bit more with parametric. We are going to now find a second derivative. So we've already learned about the first. We have a new arc length formula. So we know that from the original and rectangular. We're going to find horizontal and vertical tangents. And we're going to talk about if the particle is moving towards or away from the x-axis or towards or away from the y-axis. Fun times. Okay, so we already knew that the slope was this change in y over the change of x, and that we could just take this y prime of t over x prime of t. So where would a horizontal tangent occur? So a horizontal tangent is when I have a slope of 0. So I have this slope of 0. So that's going to be when dy dt is 0, as long as that denominator is not 0. So remember, if it's 0 over 0, we're at rest, and that's an indeterminate form. And so that's not a slope of 0. So slope of 0 is just when the numerator is 0, but the denominator is not. And a vertical tangent is going to occur when the denominator here is 0, because that's an undefined. So if I have like some number over 0, that's an undefined slope. Then that would be, well, that's a vertical tangent. Pretend like that's vertical. Okay. But a vertical tangent is when that dx dt is 0, but the dy dt is not. And people always forget to check that this piece is not 0. So don't forget about that, because when they are both 0 simultaneously, remember the particle is at rest. So then the other thing is how to find the second derivative. So you're going to get the first derivative, and you're going to derive that. So this is what I like right here. So derive with respect to t, the first derivative, and then this is the tricky part. So this is kind of like the implicit, what you've already learned, but then the tricky part is then you have to divide by that dx dt itself. So that's what we really want to look at. Okay, we'll get to some of those. So let's start looking and see if we can see where the particle is at rest. So let's review that. So particle at rest, I need the first derivative for both of these guys. And I need to see where they are both 0 at the same time. This one is at 0 and 2. Factor out a 6 here, make my life a little bit easier. Please, please, please do not just write what I write. If you need practice factoring, you do that. So I get 2 and -1. So the only place where they are the same is 2 only. Okay, second derivative. So the first thing we need to do is find the first derivative, dy dx. So we're going to take the derivative of the y with respect to t over the derivative of the x with respect to t. Dx. So I'm going to take the derivative of this guy and put it in the denominator, and the derivative of this guy and put it in the numerator. So that's not too bad. Now, to find the second derivative, I take the derivative of this and then divide by my dx dt again. So to find this derivative, now I have to do a quotient rule. Low, d high, minus high, d low, all over low low. So that is just so far that piece. So I still have to remember to divide. Oh, I think I forgot to say low, low, sorry. I still have to remember to divide by that dx dt piece. So let's simplify. I'm going to distribute. So let's see, this would be negative 6t plus 12t squared. This would actually be a negative, and a negative is a positive. So plus 2 minus 6t squared. Putting all that together, 6t squared plus, just kidding, minus 6t plus 2 all over this. Remember, when we divide by, we can put it all together now of cubed. And feel free to factor out a 2 here, but it really doesn't help me much, so I'm going to leave it. Okay, wants me to find the slope and the concavity at t equals 2. So let's check off that slope first. For the slope, I take the derivative of just the y and the derivative of just the x. And I see that these guys cancel, and I can move these negatives. So if I want to find now the derivative when t is 2, or the slope, I mean, when t is 2, that's the square root of 2 over 1, which is the square root of 2. So there's my slope. So now I need to take the second derivative. So I derive that and then divide by this again. So I'm going to go low, d high, minus high, d low, all over low, low. And I still have to divide by this guy. So divide by, I can just go ahead and put it in the denominator. So we can clean this up a little bit. Take out a 1/2, and then all the 1/2s can cancel, so that's nice because it kind of goes into both. And it's up to us how far we want to go. To simplify, I can go ahead and plug in 2 now if I want. Or I could simplify with the negatives, but if I plug in 2, what's nice is though that goes to 1. That is 2 to the negative 1/2. 2 to the 1/2 times 1 all over 2 to the negative 1/2 times 1 again. So I'm going to go ahead and put those together. So it's kind of my heartbreaker. So those go to 1 minus 2 to the first, which would be negative 1. So a negative is less than 0, so I know that the cavity is concave down. Oops, I forgot to say here, t equals 2, but I fixed it. Okay. Otherwise, I would have been wrong. I would have taken up points. Okay, let's do a tangent line. Go away. So here it gives me the position, and I want the equation of a line tangent when t is 2. So let's find our point. So I get out 6 and negative 7. So I have my point of 6, negative 7. Now we need to find our slope. So let's just find the derivative first. And then we can go plug in when t is 2. See, I remembered this time. Thank you. 412, 5. And then I can write the equation of my tangent line. Y minus y1 equals m times x minus x1. Not too bad. All right, so this is one of my favorite pieces to talk about the motion, because it's kind of the most applicable. Not that slope and tangent lines aren't pretty cool in themselves, but here, if I have, we're going to think this through. If I have where y is greater than 0, so y greater than 0 is everything up here. So I have something up here. And I know that my derivative of y is positive, telling me I am moving up. So if I am above the x-axis and I am moving up, then here I can say that this curve is moving away from the x-axis. So what if I was instead below? So I have some value below, but my derivative is still positive, so I'm moving up. Now I am going towards the x-axis. So what if here I had my y was in the negative, and now the derivative of y is less than 0, meaning I'm going down. Then now, again, I am moving away from the x-axis. So back up in the y greater than 0, and my derivative is telling me I am moving down. Then now I am moving towards the x-axis. So I want you to pause me and see if you can think through these 4 with the x derivatives and the positions. And let's see if you get those right. So when you're ready, unpause me and I'm going to fill these in. Oops. Away from y-axis towards y-axis. Away from y-axis and towards the y-axis. So if you notice, anytime I see something with the same sign, like less than, or greater than, I know that that is an away. And when I have the opposite signs, I know that that is moving towards. Okay. So let's go do an AP example here. For t greater than 0, I have the position function. They gave me an initial point, so we've done this one actually before. So we have talked about that one, but now we kind of have some different questions we're going to ask. Part A wants to know, is the particle moving towards the x-axis or away from the x-axis? Towards the x-axis or away from the x-axis at t equals 2. So to find that, we are worried about the y part. Okay? So the y at t equals 2 was -5, they told me. So that one is less than 0. So what about the derivative of y when t equals 2? That equals the sine of t all squared, which I know that has to be greater than 0 because I'm squaring. So now I have opposite signs, so we are moving towards the x-axis. So that started with a y value that was in the negative, moving up towards the x-axis. Okay, part B. See if you guys can do this one on your own. When you're ready, check with me. Okay, so talking about the y-axis, so we have to look at the x values. X of 2, it told me was, I just lost it, 1, which is greater than 0. And then x prime of 2 here is 2 over e squared, which is also greater than 0. So therefore, we are moving away from the y-axis. So the next thing we're going to talk about is the arc length equation. And we had learned this arc length equation for rectangular. And what I'm going to do is I'm going to show you the proof. You don't have to have it memorized, but it's sometimes really fun to see of how we're going to convert that arc length equation into a parametric. So I'm going to rewrite, instead of saying just that f prime, I'm going to say that that's dy dx. So then once I know that's dy dx, I'm going to go ahead and say dy dx is the same as dy dt over dx dt. And then I'm going to say, hey, this 1 is the same as dx dt squared over dx dt squared. So now I have a common denominator because I can square both of those. So I've got a common denominator. So I'm going to put my common denominator, and then I have my numerator. Now the other weird thing that we're going to do at this step is we're going to rewrite that dx as dx dt times dt. Do you see how those kind of cancel to a dx? Okay. So now I'm going to take that dx dt and rewrite it as dx dt squared square rooted. Now these guys cancel, and I'm left with our formula that we need for parametric now. Isn't that cool? So much fun. Okay, so this is the parametric arc length. This is what, I don't know why I don't like that color. This is what, oh, that's even not clear. This is what we really want to know. So we need to not only have the memorized rectangular arc length, but now we have to have the memorized parametric arc length. And so, I mean, you can think of that as x prime of t squared and y prime of t squared if you like that better. Okay, so this wants me to find the length of this asteroid from 0 to 2 pi. And a lot of times when you're finding length, you really want to graph these because they can cancel out, they can do weird stuff, and we have to use symmetries. So let's go ahead and graph. So let's start with some t values and see where I get for x and y. Let's start when t is 0. So cosine of 0 is 1. 1 cubed is 1. And sine of 0 is 0. As I graph this, I know I am at this point right here when t is 0. Okay? Let's go to pi over 2. So x here, cosine of pi over 2 is 0. And then we're going to cube it, and we get 0. Sine of pi over 2 is 1. Cubing it, we get 1. So we're up here now. Let's go to pi. Cosine of pi, -1. -1 cubed is still -1. Sine of pi 0 cubed is 0. Okay, let's go to 3 pi over 2. See what you get out. Plug them in. Okay, so this one actually looks, this asteroid looks kind of like this. And so if I want to find the length of the asteroid, we have some options here. We could find this length and multiply it by 4. Or we could find just the top half and multiply it by 2. Or we could try to go all the way from 0 to 2 pi. And sometimes that works, sometimes it doesn't, and let's find out why. So, to find the length, I need to find the first and second derivatives. I'm going to take the chain rule. So then we're going to set it up. And here I'm going to leave my A and B blank for now, just so we kind of know. Well, let's talk about if we want 0 to 2 pi. Let's go ahead and put that in, because it did say 0 to 2 pi, and let's see what happens. So I'm going to square all of that. And I'm going to square all of that. So now I'm going to go ahead and factor some stuff out, and let's see what happens. I can take out a 9, a cosine squared, and a sine squared. And I'm left here with cosine squared t plus sine squared t. And how great is that? Because that is just 1. So then this would become 3 times the absolute value of sine and cosine dt. So if I went from 0 to 2 pi, again, it's kind of making it a little bit more challenging for me because I'm only wanting that top half. So I'm going to go ahead and go from 0 to pi over 2 and multiply that by 4. That way I don't have to think through the absolute values of trying to get two separate functions. And now this is an easy use of. 0, 1 now, of u du. And notice, if I would have kept that 0 to 2 pi, when I did my u as sine, I would have had sine of 0 was still 0, and sine of 2 pi would have been 0 too. I would have went 0 to 0 and found a length of 0. So that would have been wrong. Okay, so that's why a lot of times, same thing if I would have said 0 to pi and doubled it. So a lot of times we have to find the correct symmetry, and that can be the most challenging. So, sorry, that was 12. U squared over 2 from 0 to 1. 6 times 1 squared minus 6 times 0 squared is 6. Okay. So total distance, when I've asked for total distance traveled, back in the rectangular form, we knew that this was total distance. But now whenever we're in parametric and it's talking about like the total distance traveled, a lot of time it's saying something like this, where it's like, hey, a particle is moving along this asteroid. You know, what was the total distance it traveled? And so we would have said 6 units of whatever. So the arc length formula is the total distance traveled. So let's try this AP example. says that we have the position. It gives me a point at 2. Oh, look, we've done this equation over and over. There's the derivatives. But it says find the distance traveled from t equals 2 to t equals 4. And I think I forgot to write this. This is a calculator active. So I know that it asked me to go from 2 to 4 of the square root of the derivative of the x quantity squared plus the derivative of the y quantity squared dt. So this can suck to put into your calculator sometimes, or maybe you're good at it, but just remember this all means sine of t to the 4th. And then if you want to leave that like that, you can, okay? So be careful if you try to reduce things with squares and square roots. Just make sure you use absolute values when needed. But I want you guys to absolutely put this in your calculator. And if you need to pause me, pause me. And this is it rounded, or you could have truncated. And make sure you can get that answer. Take this time and make sure that you can do this calculator skill. If you can't do it here, you can't do it on the test. And this one, go ahead and see if you can do. You can either get it rounded or truncated to this, but I want to see if you can get that one on your own. Okay, I want you to try this one on your own as well. And I want you to try this one on your own as well and see how you do. And if you don't get any of those answers on your own, then let's talk about them in class. Okay? And that's it for this day. Polar is coming up next.